Good evening, students. So today we'll take up the new chapter, that is nuclei. In the last chapter, you have studied about the concept of the atom. And in that, you know that the entire mass of the atom is concentrated at the center. The entire mass of the atom is concentrated at the center. This portion is what we called as the nucleus. So in this chapter, we are going to deal about the study of the properties and the phenomena exhibited by the nucleus. Now, by the concept of the Rutherford's alpha scattering experiment only, you have established that the entire mass of the atom is concentrated at the center with positively charged. What is that center part portion? We call it as a nucleus. So this is the nucleus. The electrons are going to revolve around this nucleus. You know that. You have studied what is the radius of this nucleus, what is the velocity of this electron, and what is the total energy of the electron when it is revolving in the nth orbit. But in this chapter, we are going to deal about the concept of this central portion, which you call it as a nucleus. And you know that this nucleus consists of a positively charged protons and neutral neutrons. So what is nuclei consist of? Nucleus consists of protons and the neutrons. Nuclei are made up of what? The protons and the neutrons. Whatever the number of protons are there in the nucleus, that is called the atomic number, denoted by the symbol Z. So what is this number of proton gives? The number of proton tells the atomic number. Atomic number, that atomic number is denoted by the symbol Z. Then, whatever the total we have, that is number of protons plus the number of neutrons, this is what we called as the mass number, which is denoted by the symbol A. So what is mass number A represents? Mass number A represents the number of protons and the number of neutrons. That is what we call as the mass number A. So what is Z represent, students? It is atomic number Z. Then what is mass number A represents? Mass number A represents both protons and neutrons. Therefore, if you go with A minus Z, A minus Z, what is this A minus Z represents? A minus Z represents the number of neutrons. What is A minus Z represents? The number of neutrons. A represents the mass number, Z represents the atomic number. So A minus Z represents the number of neutrons. A is protons plus neutrons. Z is the protons. So protons plus neutrons minus protons is equal to the number of neutrons. So what is A minus Z represents? The number of neutrons. So any nuclei is usually represented by the symbol ZXA. This X represents the name of the element. This A represents both proton number plus neutron number. Z represents the number of protons. Therefore, A minus Z represents the number of neutrons. This is what the nucleus consists of. So mainly the nucleus consists of protons and neutrons. This collectively we call it as a nucleons. So the protons and neutrons together we call it as a nucleons. It is collectively called as the nucleons. Yeah. Now related to the nuclei, you have to study the different types of nuclei. Let me know the different types of nuclei. The first one is isotope. Now, what are the isotopes? Look at this example, student. Can you tell me between this H hydrogen atom, you can observe that the atomic number are same. Atomic number are same. But look at the mass number. Look at the mass number. Mass number are different, but atomic number are same. So the nuclei having same atomic number, the nuclei having same atomic number, but different mass number. This nuclei, what we call as an isotopes. So what are isotopes? Isotopes are the nuclei having the same atomic number, but different mass number. Those nuclei are what we called as the isotopes. Now, the second one, you can see another example here, that is for oxygen. For oxygen, the isotopes of oxygen, 8O16, 8O17, 8O18. So atomic number 8 are same, but the mass number are different. So same atomic number, different mass number is what we called as the isotopes. Got it? Yeah. Coming to the second type of nuclei, that is isobars. So which is the second type of the nuclei? Isobars. So in this example, I will look, student. Here the elements are different. H, helium, carbon, nitrogen, oxygen, fluorine. But I will look on the mass number. You can see the mass numbers are same. But atomic number are different. Same mass number, different atomic number are called isobars. So what are isobars? Isobars are the nuclei having the same mass number but the different atomic number. So the nuclei having the same mass number but the different atomic number are called as an isobars. You can have the example. 1H3, 2HE3. Look at the second set of the example. 6C14 and 7N14. So mass number will be the same, but the atomic number are different, 6 and 7. In the oxygen and the fluorine, you can see the mass numbers are same, that is 17, but the atomic number are different, that is 8 and 9. So this type of nuclei, we call it as an isobars. Take up the third type of the nuclei, student, that is isotones. What are isotones? The nuclei having equal number of neutrons. You know how to calculate the isotones. I mean neutrons. That is A minus Z. A minus Z gives the number of neutrons. A minus Z represents what? The number of neutrons. So isotones are the nuclei having equal number of neutrons. Look at this example, student, that is between beryllium and boron. Between beryllium and boron, can you tell me how many protons, how many neutrons are there in the beryllium? 9 minus 4, 5. In the boron, 10 minus 5, 5. So between the beryllium and the boron, the number of neutrons are same. Number of neutrons are same. Such nuclei, we call it as an isotones. So isotones are the nuclei having same number of neutrons. Now look up this carbon and the nitrogen. In the carbon, the number of neutrons you can notice here is 13 minus 6, that is 7. Between the nitrogen, that is 7 and 14, 14 minus 7 will be the 7. So 7 and 7 are equal. That means the number of neutrons in carbon and nitrogen are same. This type of nuclei, we call it as isotones. Yes, students, how many types of nuclei we have? Isotopes, isobars, and isotones. In the isotopes, same atomic number, different mass number. In the isobars, same mass number, different atomic number. But in the case of the isotones, same number of neutrons are there in the isotones. Yeah. Now, next thing, let me take up the properties of a nucleus. Let us take up the properties of nucleus. The first one is nuclear radius. Student, you know that the nucleus consists of what? The protons and the neutrons. What is this protons, neutrons together called? Mass number A. Now, can you tell me what will happen to the size of this nucleus if I go on increasing the mass number? If I go on putting the mass number, what happens to the size of the nucleus? The size of the nucleus will increases, right? So you can tell the volume of this nucleus increases with mass number. So nuclear volume is proportional to mass number A. So nuclear volume is directly proportional to the mass number A. What is nuclear volume? 4 by 3 pi r cube. That is proportional to A. Anyway, constant is there. You can remove that because of proportionality itself. So you can tell r cube is directly proportional to A. Or you can say R is directly proportional to A power 1 by 3. To remove this proportionality constant, we are introducing a constant like R equals to R naught into A power 1 by 3. So this is the formula for the nuclear radius. So if you know the mass number A, you can find the nuclear radius. How to calculate the nuclear radius if you know the mass number? That is R equals to R naught into A power 1 by 3. What is this R naught? R naught is a constant. R naught is a constant. That value is equal to 1.2 Fermi. So 1 Fermi is how many meters? 10 power minus 15 meter. 1 Fermi equals to how many meters? 10 power minus 15 meter. So this is how we are going to find the radius of the nucleus. Please remember, students, If you know the mass number, you can find the nuclear radius. So the nuclear volume is nothing but 4 by 3 pi r cube. Now you can substitute this r value here. So you can tell that the nuclear volume is directly proportional to A, vice versa. Both are one and the same. Yes, this is about the nuclear radius. Now, let me talk about the nuclear mass. How to calculate the nuclear mass? How to calculate the nuclear mass? Students, you know that the nucleus consists of what? Nucleus consists of what? The protons and the neutrons. Now, what is the mass of the nucleus then? How to calculate the mass of the nucleus then? Mass of the nucleus is nothing but the total mass of the proton plus the total mass of the neutron, right? Let us assume mp is the mass of the proton and mn is the mass of the neutron. What is mp? mp represents the mass of proton, mn represents the mass of neutron. So in general, the nucleus consists of how many protons? Z number of protons. So it is ZMP. So what is ZMP gives? ZMP gives the total mass of the proton. Mn is the mass of one neutron. Then you can take A minus Z. A minus Z represents the total number of neutrons. So if you know the total number of neutrons, how to calculate the total mass of the neutron? A minus Z into Mn. So how to calculate the nuclear mass, students? It is ZMP plus A minus Z into Mn. This is called the nuclear mass. So if you know the atomic number and the mass number, how to calculate the nuclear mass? ZMP plus A minus Z into Mn. So this is called as the nuclear mass, students. Now, if you know the nuclear volume and the nuclear mass, how to calculate the nuclear density? The basic definition for density is mass by volume. So how to calculate the nuclear density? Nuclear density is given by the formula nuclear mass divided by the nuclear volume. So mass of the nucleus divided by the volume of the nucleus, this ratio is what we call as the nuclear density. And please remember, this nuclear density will be independent of the mass number. Why, sir? You know the nuclear mass is given by ZMP plus A minus Z into Mn. But mass of the proton is almost comparable with the mass of the neutron. Almost they are same. Let us say that is equal to M. Then what will happen to this equation? Zm plus A minus Z into M. So that will become AM minus Zm. So Zm will get cancelled out. The remaining value will be A into M. So this is the nuclear mass. You know what is the nuclear volume? 4 by 3 pi r cube. You know that r cube can be taken as r naught into a power 1 by 3 whole cube. So this 3 and this 3 will get cancelled out. Remaining will be a. This a and this a also will get cancelled out. So clearly this tells the density is independent of the mass number. Nuclear density is independent of what? Mass number. If I double the mass number, if I increase the mass number by 4 times, 5 times, the nuclear density will not change. The nuclear density will not change. The nuclear density will remain same. And please remember, students, this density is very large. This density is very large, and that is in the order 10 power 17 kg per meter cube. So what is the order of the nuclear density? 10 power 17 kg per meter cube. And please remember, this nuclear density is independent of the mass number A. So density will remain same for all the atoms. Students, let me take the hydrogen 1H1 and I will take the helium 2He4. Let the density of hydrogen is ρ1 and for helium the density is ρ2. Can you tell me what is ρ1 by ρ2? Can you tell me the value of ρ1 by ρ2? Yes, ρ1 by ρ2 ratio will be equal to 1. No, because it does not depend on the mass number. It does not depend on the mass number. For irrespective changes in the mass number, the density will remain same. So for all the elements, for all the atoms, the density will remain same. So let us go to the next concept, student, that is nuclear force. Nuclear force. So inside the nucleus, what we have, students? We have protons and neutrons, isn't it? And inside this nucleus, these protons and neutrons are strongly bound by an attractive force. Strongly bound by an attractive force. That attractive force is what we called as the nuclear force. So please remember, nuclear force is the strongest force in nature. So inside the nucleus, whatever the protons and neutrons are there, that protons and neutrons are strongly bound by an attractive force. That is what we called as the nuclear force. Now, what are the properties of the nuclear forces? What are the properties of the nuclear forces? Yeah. See here, if I say this is the nucleus, here the protons, neutrons are there. Let us say the blue color dot will represent the protons and the red color dot will represent the neutrons. Now, the first property you have to remember, this nuclear force is a short range force. I mean, if the two nucleons are separated by a small gap of Fermi, Fermi means 10 power minus 15 meter, then only the nuclear force will come into picture. Suppose if the distance between the two nucleons is increased, then the nuclear force will not come into picture. At that case, the electrostatic force will come into picture. So, nuclear force is going to exist only if the two nucleons are going to be very, very close to each other, if they are separated by a distance of 10 power minus 15 meter. So only we call it as the nuclear forces or a short range force. And no doubt, the nuclear forces are strongest force in the nature. You know that which is the weakest force? Gravitational force. So which is the strongest force in nature? Nuclear force is the strongest force in nature. So nuclear forces are strongest force. And also remember, the nuclear forces are attractive. Nuclear forces are an attractive force. And please remember, the nuclear forces are charge independent. Charge independent means the nuclear force does not depend on the charge. So if I calculate the force between the two protons, or force between the proton and the neutron, or if I calculate the force between the two neutrons, all these three forces are equal because charges, nuclear forces are charge independent. So whatever may be the charge, see here, neutron is not having the charge only, but there will be a force between the two neutrons or the force between the proton and the neutron. I mean to say that if you change the charge, then the nuclear force is not going to affect, it will remain the same. Therefore, the nuclear forces are going to be considered as a charge independent. So, force between two protons, force between the proton and the neutron, and the force between the two neutrons will be the same. Look at the next point, student. The nuclear forces are a non-central force. Nuclear forces is a non-central force. I mean, the force is not acting between the two centers of the particle. The two centers, whatever we have, the force is not acting between the two centers of the nuclei. That is what we considered as the non-central force. So what are non-central force? The force which is not acting between the two centers of the nuclei. Since it is not acting between the two centers of the nuclei, it is considered as a non-central force. And also remember, nuclear forces are exchange force. So there will be an exchange of pi mesons. There is a pi particles. These pi mesons are going to exchange between the nuclei. Because of this exchange of this pi mesons only, the nuclear force is going to be existed. So the nuclear forces are considered as an exchange force. So nuclear forces are exchange force. So these are the important properties of the nuclear force, students. So nuclear force are short range force. They are strongest force in nature. They are attractive, and the nuclear forces are charge independent. The nuclear forces are non-central force, and nuclear forces are exchange force. Yes. Come to the next concept, that is atomic mass unit. AMU. Student, please remember, whatever the nucleus we have, that is proton and neutron, that is very, 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 very small in size. You know the size of the nucleus. Size of the nucleus is 10 power minus 15 meter. You can imagine how small it is. Since it is a very small, so whatever the protons and neutrons are there inside that nucleus, that values are also still less in mass. Because of that reason, we cannot express the mass of the nucleons in terms of gram or kg. So in order to avoid that, we are using another important unit, which we call it as an atomic mass unit. Atomic mass unit is the unit used to represent the masses of the nucleons. Used to represent the masses of the nucleons. Masses of nucleons. So what is atomic mass unit? Atomic mass unit is the unit used to represent the masses of the nucleons. And please remember, one AMU, one atomic mass unit, is also defined as 1/12 of mass of one atom of carbon-12 isotope. 1/12 of mass of one atom of carbon-12 isotope. Now, after substituting the Avogadro hypothesis that you have studied in chemistry, I think in the first year, that is in the 11th standard. So by substituting that, you can get the relation between AMU and Kg. Please remember, 1 AMU is equal to how many kg? 1.66 into 10 power minus 27 kg. 1 atomic mass unit is how many kg? 1.66 into 10 power minus 27 kg. And you know Einstein's mass energy relation, that is E is equal to m into c square. So if any nuclei is having a certain mass, then this mass can be converted into a energy. How to convert this mass into energy? By using the formula E is equal to mc squared. This is what we called as the Einstein's mass energy relation. And please remember, if this mass is in kg and c is the speed of light, then you can get this energy in terms of joule. But there is another unit for energy which you know that which is going to be represented with electron volt. So this you have studied in the second chapter itself, students. Electron volt is the unit used to represent the energy. But the condition is this mass should be represented in AMU. It should not be in kg. It should be in atomic mass unit. Then the corresponding energy what we are going to get, that is going to be expressed in terms of electron volt. And please remember, 1 electron volt equals to how many joule? 1 electron volt is equal to 1.6 into 10 power minus 19 joule. 1 electron volt equals to how many joule? 1.6 into 10 power minus 19 joule. Suppose if you want to calculate the energy associated or equivalent in 1 AMU, if you consider the mass as 1 AMU, energy associated in 1 AMU is equivalent to 931 mega electron volt. So what is the energy equivalent to 1 AMU? Energy equivalent to 1 AMU is 931 mega electron volt. 1 atomic mass unit is equivalent to how many mega electron volts? 931 mega electron volts. Got it? That is the energy associated in 1 AMU. Come to the concept of the mass defects. So mass defect delta M, what it represents? Student, if you consider a nucleus, you can find the mass of the nucleus. Let M is the mass of the nucleus. M is the mass of the nucleus. Now you can find the nuclear mass. How to calculate the nuclear mass? That is mass of the nucleons. That is ZMP plus A minus Z into Mn. So by knowing the number of protons and number of neutrons, by knowing the number of protons and the number of neutrons, you can find the nuclear mass. The ratio of this nuclear mass and the mass of the nucleus, this difference, because these both are not going to be the same, there is a slight difference value. That difference is what we called as the nuclear mass, mass defect. So how to calculate the mass defect? The difference between the nuclear mass and the mass of the nucleus is called as the mass defect. So how to write the mass defect delta M? Delta M is nothing but ZMP plus A minus Z into Mn minus M dash. This is the mass defect. So what is mass defect? Delta M, ZMP plus A minus Z into Mn minus M dash. This is called as the mass defect. Remember this formula, which is going to be important for the problems. Now, if you know that the mass defect, let me know the next concept, that is the binding energy. What is this binding energy? What is this binding energy? Suppose if I consider a heavy nuclei where it contains many number of protons and neutrons, where it contains many number of protons and neutrons. Now, you can split this nucleons and you can divide. You can separate that. Whatever the energy you require to separate all the nucleons into an individual, that energy we call it as a binding energy. Reverse is also possible, vice versa. So if there are some nucleons or like this, now you bring all these nucleons together to form a stable. To bring all the nucleons to form a stable, that energy is also called as the binding energy. So what is binding energy? Binding energy is the energy required to bind all the nucleons to form a stable nucleus. The energy required to bind all the nucleons to form a stable nucleus is called as the binding energy. Then what's the formula for this binding energy? This binding energy is given by the formula, the mass defect delta M, the mass defect delta M into 931 mega electron volt. Delta M into 931 mega electron volt. So binding energy is nothing but delta M into 931 mega electron volt. That is what we considered as the binding energy. So binding energy is nothing but mass defect delta M into 931 mega electron volt. Student, you can observe here, this is represented in electron volt, means this mass defect must be in AMU. Mass defect must be in AMU, that is atomic mass unit. So this is what we call as the binding energy. Yeah, 931 into mega 931 delta M into 931 mega electron volt. Then binding energy per nucleon. Instead of calculating for the entire nucleon, if there are n number of nucleon here, for all this n number of nucleon to bind, that energy we call it as a binding energy. If you calculate the binding energy by mass number A, that is what we call as the specific binding energy. So what is specific binding energy? Binding energy per nucleon. So binding energy by mass number is what we called as the specific binding energy. So if you calculate the binding energy the binding energy per nucleon is considered as the specific binding energy. So binding energy by mass number is considered as the specific binding energy. Then you know that the binding energy is nothing but delta M into 931. For this, if you divide by mass number, that gives the specific binding energy. Student, what is the application of this specific binding energy, which you considered as a binding energy per nucleon? Actually, by knowing the binding energy per nucleon or a specific binding energy, you can know the stability of the nucleus. So binding energy per nucleon actually measures what? The stability of the nucleus. That is the application of the binding energy per nucleon. More binding energy per nucleon, the nuclear stability is more. More the binding energy per nucleon, more will be the stability of the nucleus. To analyze the stability of the different nuclei, we are having a curve. What is that considered as the binding energy curve? Binding energy curve. What is this binding energy curve tells? Binding energy curve is the curve obtained by plotting the binding energy per nucleon, or you can consider as a specific binding energy. Specific binding energy along y-axis and mass number along x-axis. This graph is what we considered as the binding energy curve. So binding energy curve is the curve obtained by plotting specific binding energy along y-axis and mass number along x-axis. This curve is what we considered as the binding energy curve. You can have a nature of the curve here. Student, observe here. This is mass number. This is binding energy per nucleon. As the mass number initially increases, this initially rises sharply like this, and it attains a maximum for a iron having atomic number 56. Hence, this element is considered as more stable. So, which element is more stable? Iron is considered as more stable because that iron is having maximum specific binding energy. From iron, if you increase the mass number A, this binding energy start decreasing like this. So, the mass number between 20 almost to 170, almost the specific binding energy will be constant. Hence, it is considered as more stable only. But if you consider the nuclei having a mass number more than this 170, all that binding energy will be less. Hence, these are considered as a unstable. But please remember, this also referred as radioactive elements. Because of more mass number, it is referred as radioactive elements. We are going to study this radioactive concept in the same chapter, but after analyzing the nuclei concepts. And if you look the mass number less than 20, what will happen for the nuclei having a mass number less than 20? For a mass number less than 20, the specific binding energy will be less. Hence, they are also considered as an unstable. Why it is considered as an unstable? Because the specific binding energy is less. Because of less specific binding energy, it is considered as an unstable. So, for which nuclei the binding energy per nucleon is more? That is specific binding energy, that is more for iron. So that are the properties of the binding energy curve. Got it? Yeah. And in order to explain the stability of the nuclei, we have one more parameter, that is what we called as the packing fraction. This usually denoted with the symbol F. This packing fraction also explains the efficiency, the stability of the nucleus. The stability of the nucleus is going to be measured by another important parameter, that is called the packing fraction, which is measured as mass defect per nucleon. Mass defect per nucleon. Mass defect means nuclear mass minus mass number divided by the mass number. This ratio is what we called as the packing fraction. So what is packing fraction measures? Packing fraction measures the stability of the nucleus. Now, you can observe here. This packing fraction is going to be a positive or negative or a zero value. Packing fraction may be positive or it may be negative or zero value. You know that the packing fraction is given by m minus a divided by a. For the carbon 12 isotope, you can find what is the packing fraction, or you can go with 8O16. You can find what is the packing fraction for this, like that. For any element, you can find the packing fraction. Depending upon the packing fraction value only, we are going to decide the stability of the nucleus. And this packing fraction is going to be 0 for a mass number 16. Please remember that also. For the packing fraction is 0 for a mass number 16. For a mass number 16, the packing fraction will be 0. So this is another important parameter to measure the stability of the nucleus. Yeah. Come to the concepts of the nuclear reaction, students. What is the meaning of this nuclear reaction? Before going to fission, let me know the nuclear reaction. Then later we can explain the difference between the nuclear fission and fusion. Now, in the nuclear reaction, you just considered one element, let us say ZXA. X represents the name of the element, A represents the mass number, Z represents the atomic number. Now, for this nucleus, if I bombard with a neutron, I'm going to strike with a neutron. If I bombard this nuclei with a neutron, then this nucleus is going to split into two parts. When it splits into two parts, there will be neutrons also. Neutrons are also produced. This reaction is what we called as the nuclear reaction. So whenever the heavy nuclei is bombarded with a neutron, it splits into lighter nuclei with the release of these neutrons. Again, this neutron is going to bombard with this daughter nuclei. Then this is going to further split into two. This reaction continues, and in each and every step of the reaction, the number of neutrons multiply indefinitely. For in each reaction, the neutrons are multiplying indefinitely. Such reaction is what we call as a nuclear chain reaction. Suppose if you control the reaction at any stage, then it is considered as a controlled chain reaction. If you are controlling the reaction at any stage, then it is considered as a controlled chain reaction. Suppose if you can't control the number of neutrons, where you cannot stop the reaction in between, intermediate. Once if the reaction has started, it has to end up with the last neutron, where we cannot stop the reaction at the intermediate stage. Such reaction is what we call as an uncontrolled chain reaction. Uncontrolled chain reaction. So there are two types of chain reaction. One is called as the controlled chain reaction. The another one is uncontrolled chain reaction. In the controlled chain reaction, we can control the number of neutrons where it is multiplying in the reaction. But in the uncontrolled chain reaction, we cannot stop the reaction at the intermediate stage. That is called the uncontrolled chain reaction. Student, this nuclear reactions we are going to differentiate into two. One is called as the nuclear fission reaction. The another one is the nuclear fusion reaction. Nuclear fission reaction, and the second one is nuclear fusion reaction. In the nuclear fission reaction, we have a heavy nuclei that is going to split into two or more lighter nuclei after bombarding with neutron, and also it releases the energy. That type of reaction we call it as a nuclear reaction. Look at the reaction example here, students. We have considered 92 uranium-235, isn't it? This is heavy nuclei. This nuclei is bombarded with a neutron. If I bombard this with a neutron, it forms 92 uranium-236. Then it becomes an unstable. If it is in uranium-235, it will be more stable. So only we are going to bombard with neutron to make it as unstable. Then this uranium is going to split into different parts, like 56 barium-141, 36 krypton-92, and 3 neutrons. It releases with 3 neutrons. This reaction is what we call as the nuclear fission reaction. Please remember the example for the nuclear fission reaction, students. 92 uranium-235 is bombarded with neutron. That forms uranium-236. That uranium-236 splits into two parts, 56 barium-141 plus 36 krypton-92 plus 3 neutrons. So 3 neutrons are released. Actually, these 3 neutrons will not remain same. This neutron is going to further bombarded with barium and krypton. That will further splits into 2 parts. So these reactions will continue. Because of this only, I am considering this nuclear fission reaction as a nuclear chain reaction. What is Q? Q is the energy released in the reaction. If you calculate the energy in this uranium-235, please remember it is of about 200 mega electron volt. So what is the energy released in the nuclear fission reaction? It is about 200 mega electron volt. Then if you calculate what is the energy per nucleon, this is called specific binding energy. Specific binding energy of this nuclear fission reaction is 0.8 mega electron volt. So please remember these two values. What is the binding energy for the nuclear fission reaction? It is about 200 mega electron volt. What is specific binding energy for the nuclear fission reaction? It is about 0.8 mega electron volt. So these are the energy released in the case of the nuclear fission reaction. Yes, students, I hope you got the concepts of the properties of nucleus, how to find the different types of nuclei, how to measure the mass of the nuclei, how to find the energy, and how to calculate the stability of the nucleus by knowing the binding energy curve. And also you got the idea about the nuclear force, and also you got the idea about the nuclear chain reaction. I hope you got this number of concepts, students. I will stop at this stage. In the next class, we'll continue the next reaction that is called the nuclear fusion reaction, and also let me know the multiplication factor of the reaction. Isn't it, students?